Have you ever wondered how a load cell works? What makes this small device capable of measuring heavy loads so accurately? Welcome to the intriguing world of load cells, the unsung heroes of weight measurement. These are specialized sensors or transducers that have the ability to convert a load or force acting upon them into an electronic signal. Now, the type of signal they produce can vary. It could be a change in voltage, a shift in current, or even a frequency change. This depends largely on the type of load cell and the circuitry used. There's a diverse array of load cells out there, from resistive load cells that work on the principle of piezo-resistivity to capacitive load cells that rely on changes in capacitance. The variety is truly impressive. But don't worry, we'll get into the specifics soon. So, with this basic understanding, we can delve deeper into the working principle of these fascinating devices. Let's start with the most common type of load cell, the resistive load cell. At its core, this cell operates on the principle of piezo-resistivity. Now you might wonder, what does that mean? Well, in simple terms, piezo-resistivity means that the resistance of the material changes when a force, load or stress is applied to it. Think of it like a sponge. When you press a sponge, its shape changes, right? Similarly, when you apply a force to the resistive load cell, its resistance changes. But unlike a sponge, this change in a load cell is converted into an electronic signal. It's like the load cell is whispering in the language of electricity, telling us how much force is being applied. Now, how does this change in resistance cause a change in output voltage? Well, think of it like a water pipe. The water flowing through the pipe is like the input voltage applied to the sensor. If the pipe narrows, the water flow, or in our case, the output voltage, changes. That's exactly what happens in a resistive load cell. The applied force changes the cell's resistance, just like a narrowing pipe, leading to a change in output voltage. So in essence, a resistive load cell is a sophisticated translator. It takes in the physical language of force and translates it into the electronic language of voltage. And that's how resistive load cells work. A simple yet ingenious principle, isn't it? Now, let's shift our focus to another type of load cell, the capacitive load cell. Capacitive load cells operate on the principle of change in capacitance. Now, what's capacitance, you ask? It's the ability of a system to hold a certain amount of charge when a voltage is applied to it. This might sound a bit abstract, but let's break it down. Imagine a capacitor like a tiny storage unit for electrical charge. This storage unit has two plates that are separated by a small gap. When a voltage is applied, an electrical charge is stored between these plates. The amount of charge the capacitor can hold, or its capacitance, depends on three factors: the area of the plates, the material between the plates known as the dielectric, and the distance or gap between the plates. So how does this relate to capacitive load cells? Well, when a load or force is applied to the load cell, it changes the gap between the plates of the capacitor. This change in the gap alters the capacitance of the system. The change in capacitance is then converted into an electronic signal, which can be measured and used to determine the applied load. In simple terms, the capacitance is directly proportional to the overlap of the plates and the dielectric, and inversely proportional to the gap between them. This means when the load increases, the gap decreases and vice versa, leading to a change in capacitance. So that's capacitive load cells for you, a different approach but equally effective in measuring loads. Apart from resistive and capacitive, there are several other types of load cells. Let's explore some of them. Load cells with column-shaped spring elements, for instance, are designed for high loads. Their robust construction allows them to withstand significant pressure while maintaining accurate measurement. Then we have hollow cylindrical load cells, perfect for extremely high loads. Their unique design allows for even distribution of force, ensuring precision even under intense stress. Next up are shear beam load cells. These devices are often used in industrial settings, known for their durability and ability to handle both tension and compression. And lastly, we have load cells with diaphragm spring elements. These are typically used in low-capacity load applications, where sensitivity and accuracy are paramount. Each type of load cell has its own unique design and working principle, tailored to fit specific applications. And there you have it, a world of load cells, each with its unique way of accurately measuring loads. Fascinating, isn't it?